Hi again, and now let's continue with convolutions and pooling. So in the previous sub-lecture we saw what makes images so special, and that in order to capture, to encode the signal that is inside images, we have to transform also our parameters. We have to enter some sort of inductive bias to make sure that the special nature of the signal is encoded. So for this, we have convolutions. And convolutions are basically very similar to sliding 2D parameter matrices or filters. Now let's start with let's try to explain them, and there is no better way than just actually visualizing first what convolutions do. So let's say we've got this input image. This image, for the sake of simplicity, comprises zeros and ones. Well, normally it's a color image, but let's say it's just zeros and ones. And then we have a convolutional filter, which is a 3x3 array. And now to perform convolution, we take this convolutional filter, we overlay it on top of the image matrix and the image array, and then we perform basically multiplication of pixel with a filter location. So 1 times 1, 1 times 0, 1 times 1, 0 times 0, 1 times 1, 1 times 0, 0 times 1, 0 times 0, and 1 times 1. And all these individual terms, we sum them up, and the result is 4. It's 4 because this is 1, plus 1, 2, plus 1, 3, plus 1, 4. Then we continue to the next location. So the convolution takes exactly the same convolution filter and slides it on the image array. So now we go to the second, we start from the second column and the first row, right? Second column, first row. We repeat the operation and we obtain a result. And by doing so again and again throughout the whole image matrix, we obtain the final convolutional output, or feature map, as we'll see later. Mathematically, this is defined as a double summation, where I here is your image and H is your filter. A convolutional, so what is actually the convolution module? What is mathematically then, how is it mathematically defined? To be precise, the convolution of two functions is denoted by this asterisk, and it's actually the integral of one image after the other one is reversed and shifted. So if we take this integral, we have actually the convolution. So now it's in the discrete domain, and assuming that we've got a finite, so one of the two functions is finite, in our case the weight parameter, this is equal to a finite weight summation, sorry, a finite double summation, right? This is the shifting part here, and this is the filter part here. The convolution operation, if we plot it, it looks like that. So if this is our signal F and this is our filter G, the convolution is going to have like this shark fin sort of shape, and in fact is very close to cross correlation. So in fact the cross correlation is the reverse of convolution, and as we will see, there is a dual relationship between forward propagation, backward propagation, and convolution and cross correlation. Autocorrelation is also quite similar. It's a similar operation. So the output dimensions after convolution are also pretty easy to derive. We can obtain them based on this formula. So the height and the width of the output is basically the same as the height of the input minus the height of the filter divided by the stride plus 1. And the stride is the amount of pixels we jump every time we do one slide, right? So we can move one pixel always to the right and one pixel always to the bottom. However, we might as well also jump, like, you know, if the filter is of size 5, we can also jump 5 pixels to the right, and then we would have 0 overlap. So this is the stride, how much you jump to the left or to the right. Typically, the depth of the convolution, so the number of channels of the convolution is equal to the number of channels, and right. So the d in and the df are equal, and the output depth is equal to the number of filters we have in our convolution. The reason why the reason that the depth of your image input and the depth of your filters has to be equal is so that they match when we're doing the number by number, entry by entry multiplications. What makes convolution special is local connectivity. So convolutions share weights spatially, right? So all these weights are unique in a way within this orange box. However, this orange box moves across the whole image plane, and you can think of this operation as having multiple rectangles all over the image plane, with, however, having exactly the same weights. So if we were to take one more rectangle here, it will have exactly the same weights as the orange rectangle here. Usually it is surface-wise local and depth-wise global. Basically, the width of your convolution filter equals to the width of your input image. Now, this is not a strict requirement. There are also the so-called depth-wise convolutions, where actually the convolutions are also shared across channels. This depends on the application. This contrasts a lot with multi-layer perceptron, so fully connected layers, where there is no local connectivity. In MLPs, everything is connected to everything. There is no notion of space, right? So if everything is connected with everything, if there is full connectivity, there is no surface, there is no space, there is no depth. In fact, if you have a fully connected layer and you shuffle the pixels of your input image, there will be virtually no difference in the output. It's like if you were to permute your entries in your weight vector multiplication. If you permute them in a consistent way, so you permute in the same order the columns and the arrays of the weight and the vector in the inner product, you would obtain exactly the same result, and that's exactly the point I'm trying to make here. Now, an interesting point to remember is that local connectivity does not mean convolutional filters, right? So for convolutional filters means that we have local connectivity as well as shared parameters. However, one can also imagine that we do have local connectivity, so our filters have this rectilinear shape, so they are local within a neighborhood. However, from one rectilinear shape to the other, we have different parameters. Then we don't share parameters. We have local connectivity, but we don't share parameters. Generally, this leads to much more expensive parameterizations, right? So for just 24 filters along the x and y axis, and for a relatively small image, we would have a lot of parameters. However, this can be useful in some applications. The applications where this can be useful is applications where the location is actually important to encode certain types of features. For instance, when we have registered faces or in some sort of medical application, one can imagine that particular location will have specific features like eyes or nose features or mouth features. Now, that is not to say that you should not share parameters for these applications. It's only to motivate when non-share weights might actually make sense. A good thing about convolutions is that they generally reduce dimensionality because this is good because they make things much more efficient. It's much easier to convolve the images in a reasonable time. However, the problem is that exactly because they become smaller and smaller, we sort of start losing spatial resolution. So we're running out of latent pixels. The problem with this is then that we cannot have really deep architectures because simply our feature maps are not large enough. What is more, this means that details are potentially lost. So by dropping pixels, so to speak, we are losing minute details that might not be always necessary for coarse classification. However, for finer and finer grained tasks, recognition might actually get hurt. A visual example of this is shown here. So it will start here with our image. After a first layer of a convolution, then our 5x5 image becomes 3x3, and if we apply one more 3x3 filter, then it becomes a single number. So within 2 layers, we have reduced our input size 25-fold. To address this problem, a frequent solution, so a solution that we often rely on, is to have zero padding. So basically, we add rows and columns around our input image containing zeros, and by doing so, after our convolution, the final output feature map retains the original dimensionality of our input image. Of course, the problem here is that our convolution starts taking into account 0 pixels. However, that is probably not a very big problem because anyways, a standalone pixel in the corner or in the edges does carry less information in the first place. Some good practices is to make sure to resize the image to have a size in power of 2. And we want to do that such that it is easy to perform convolutions with the numbers making sense in terms of striding and sliding through the image. It's good if the stride is equal to 1. That makes things much simpler in terms of making things work in terms of engineering. But also stride of s equal 1 actually gives the best results typically. And quite often a small filter of 3x3 works very good with deep architecture. So when you don't have a very deep architecture, 3x3 might not be the optimal choice. Maybe it's too small. But with deep architecture, 3x3 is typically a really good choice. Also adding a layer of 0 padding is very useful for many applications, especially for deeper architectures. We were going to discuss about deeper architectures in a later lecture. Some further general good practices is to make sure that we avoid combinations of hyperparameters that in general they don't click. And what do I mean by that? Let's assume now this following example. Let's assume we've got a convolution of stride 2 with a parameter shape matrix of size 3x3. Let's assume that our image size is 6x6, and then if we do the calculations, we will derive that output and width, our height and width of our output will be a decimal number. So obviously this is not acceptable. It leads to programmatically worse results, worse accuracies. The reason is that boards are ignored and generally things become more complicated. So visually this looks like as follows, right? Like this is our convolutional filter, and if we move one step to the right, then it's still okay. However, if we move further, like by 2 pixels, then without zero padding, we cannot really define the convolution no more. And of course, this is a problem across all the edges of our input. Another very important operation that is very closely connected to convolutions, at least in terms of like order of operations, is pooling. So typically after convolutions and perhaps non-linearities, pooling follows. And pooling simply aggregates multiple values in a small neighborhood into a single value. This is it. It allows to bring some invariance to small transformations and perturbations. So let's say there is some sort of pixel shift in the x or y dimension. With pooling, we make sure that we don't get disturbed, like the neural network doesn't get disturbed too much at least. Furthermore, pooling reduces feature map size, which makes computations much more efficient and much faster. And also, it makes sure to keep the most important information for the next layer. So we do not saturate our next layer with too many correlated and irrelevant values. The two most popular types of pooling is max pooling and average pooling. Max pooling simply takes the maximum over a local neighborhood. Average pooling simply takes the average over a normal neighborhood. The gradients of max and average pooling are also pretty simple, so that's also nice. In general, one more thing to tell about convolution layers is that in general there is no dropout. We can do it, it's not like you cannot do it, but probably it will not give you much, maybe it will even hurt you. The reason is that convolutional filters are much sparser weight arrays, so compared to fully connected layers, you don't really have that many parameters. So there is no room for codependency to develop between neurons. Moreover, it will be more like dropping out single pixels, which means that there is too little influence to the final result, and this means that likely dropout will not contribute. Moreover, convolutions are by definition operations that capture local correlations, right? So this means that if we use dropout with convolutions, then these local correlations get disturbed. In effect, we render our own convolutions ineffective and probably they don't make sense anymore. Thank you.